episode 30, Stardust or Pile of Cosmic Poo? And welcome to another edition of the Syzygy podcast. My name's Chris Stewart, sitting opposite me at the microphone as ever, Emily Brunsden. Hi, Emily.
Hello, hello.
So, 2019 is apparently the International Year of the Periodic Table. I didn't know that until you sent me a link the other day saying we should do a podcast about this periodic table. Did you know that?
I did know that, yes, because there's been all sorts of wonderful international years of, and I always keep my eyes and ears open for good things that I'm going to be really involved in. We had the International Year of Light.
Yeah, there was that.
International Year of Astronomy. That was a good one.
But if you'd asked me, a month ago, so 2019, what do you think it's going to be the International Year of? I wouldn't have picked the periodic table. But these things invariably come around because there are big anniversaries. So the 100th anniversary of Einstein's big year where he published, 3 or 4 or 5 really big papers that changed the way we see the world. That was back in 2007, 2008. And that became International Year of Physics and everyone went mad for Einstein. This year, International Year of the Periodic Table, because it's 150 years since Mendeleev first put all the atoms, all the different elements that were known, because we didn't really know much about atoms at the time, 150 years ago, but took all the different elements that were known at the time and said, I can see a pattern here. This is not just a random collection of stuff. I can put them into a table, and tables are always good. So how does that work? We're going to delve into that a little bit today. We're going to talk about the periodic table, but in particular, it's not just the story of stuff and matter and, atoms and things. It's actually also the story of astronomy. It's the story of stellar evolution. It's the story of where all this stuff came from. So that's what we're going to be talking about today. But before we get down there, Emily, I just saw in the news the other day a little bit of sad news. We need a bit of sad violin music in the background here for this one, because I saw a report in Scientific American, I'll link to it in the show notes, that says that opportunity is gone to sleep and is probably not going to be waking up.
Yeah, this is really sad. We have kind of known for a while, so this is kind of similar to if you have a terminal illness. We knew that. We
saw this one
coming.
We
knew that Opportunity had a terminal illness.
Now this is Opportunity, the little rover on Mars, which has been going for 15 years. 15 years? And it was originally, we'll be, if it goes for 3 months, we'll be happy. And 15 years later, it was still going. But what happened?
Well, we had an enormous dust storm on Mars. And ever since then, we've been really not sure if Opportunity's made it. Even Curiosity, the much, much newer rover on Mars, had issues after the dust storm. So it's unsurprising that finally, after this mega, mega dust storm, Opportunity's solar panels got covered in dust and it just basically couldn't recharge its batteries after that.
Yeah, that's death to a rover, right? If you can't get any energy from the sun, there's nothing you can do. There's no way that you can come back. And for months now, that was back in the middle of 2018, wasn't it? And for months now, the NASA people who have been looking after this mission have been sending out messages across the void saying, Opportunity, you're still there, hello, and trying all sorts of different commands saying, try turning it off and on again, try turning your camera this way, try just anything, hello, is there anything? And nothing's coming back. And so it sounds like they're finally in a position to say, you know what, I think we need to call this one a day, which is really sad because this thing's been going for a decade and a half. There have been people who've been working on this for a good part of their working lives and saying goodbye to this funny little machine who's been crawling around on the surface of Mars, covering the distance in 15 years of about a marathon. So it's not been moving terribly quickly, but that's a long way.
It's a long way
on
for
another
a rover.
planet. Yeah,
it's a very, very long
doing
way.
amazing science, making all sorts of discoveries. For it to finally go quiet, that's a very sad day. So, yeah.
We're going to miss you.
We will. Bye-bye, Opportunity. Fortunately, there are still a few other rovers up there doing their thing. There's Curiosity still up there. And the latest one, Insight.
Yes.
It's not a rover, is
lander.
it? It's a lander, but it's got all sorts of instruments bringing back all sorts of crazy and great data. So we're not done with Mars yet, but farewell, Opportunity. It's been a lovely ride. Listen, on to the big subject du jour, the periodic table. So I guess before we really get onto the astronomical side of things, let's just talk briefly about what is this thing called the periodic table. Emily, let's start with that. Take us through that. What's the periodic table?
There's antimony, arsenic, aluminum, selenium, and hydrogen and oxygen and nitrogen and rhenium, and nickel, neodymium, neptunium, germanium, and iron, americium, ruthenium,
Well, it's
uranium,
actually a little bit like if you decided one day to take all of your clothes out of the closet, sort them all into the different categories that you have, and then fold them up really, really neatly and put them all back in your drawer in a really nice, orderly way so that the socks were together, so that your trousers were together, but then they were color-coded and organized by season, by weight. It's kind of a bit like that.
Okay, that's never going to happen in my life, but I like the analogy. Well done. I've never heard that analogy for the periodic table before. I like it. So it's organizing stuff.
Yes,
right?
Yeah. And so what it is, and we've got I must be upfront, we've got a chart in front of us here, so we can cheat and have a look at the periodic table.
Yeah, we haven't got all this committed to memory, or at least I haven't. When I was in high school, we had to memorize the first 20 elements, and I can remember the first 4. That's about it. Yeah.
I can do a little bit better, but not much. But what we have is basically we got 7 rows in the periodic table, and then we've got columns. And so the rows and the columns are organized, and they're organizing the chemical elements by their different properties. And there's 3 key things that we organize them by. So we organize them by atomic number, which is the number of protons that they have in the nucleus. So we go from 1 all the way up to, I think we're up to 118.
Sounds about right, yeah.
We have those in order. We also arrange them by electron configuration. And this is why the periodic table sort of splits. It kind of has a slightly U shape in it, because it's not about the number of electrons that you have in your atom. It's about how many more you have to go before you fill up a particular level. And so sometimes that's only 2, and then sometimes that's more.
Yeah.
So that's why they're organized in that way.
So the periodic table, just at its most basic level, it's organizing the stuff that we find around us in the world. And by stuff, ultimately we figured out we're talking about atoms, different kinds of atoms. And scientists realized over many, many years that if you break stuff down, you can find things which are hydrogen, and that's a kind of atom. And you can find carbon, and that's a kind of atom, and oxygen. And if you look at those very, very carefully, you find patterns in them. And what we ultimately realized was that those different atoms, not only do they have different properties, but those properties are related to how those atoms are composed, how many protons they have in their nucleus, positively charged protons, and how many electrons they've got going around the outside, the negatively charged electrons. And so it's the periodic table is a combination of the atomic physics, how the atoms are put together, and then the chemistry, how those atomic configurations fit together and react in different ways.
Yeah, and there's a bit of a weird terminology that we use as well. So we talk about elements because they're kind of elementary, these atoms. So another word for atoms that we use is elements. And particularly in astronomy as well, we use chemical elements. So they're not chemicals as you have under your sink. They're actually individual species of these different atoms. So They're not complex things that we're going to find out cleaning bleach or something out in space. They are individual things like carbon and oxygen.
Yeah, so you can have individual atoms of a particular element. Hydrogen is an element, helium is an element, carbon is an element. You can put those different atoms together to make molecules and so on. Anyway, so that's the basics of the periodic table. So we've got this table which is organizing things by atomic structure and by similarity in its chemical reaction and how it behaves in the world. And so you end up with these rows, which is talking about increasing numbers of protons in these atoms. So as you go up through the periodic table, you're getting more and more protons in the nucleus. And then you've got columns, which are talking about how similar groups of elements, similar kinds of atoms behave in the world, how they behave chemically with each other.
Yeah, and that's very useful. So you can take, for example, the very last row, because they've got their shells all filled up with electrons. That means that they're not really interested in what other chemical elements are doing around them. They're not interested in trading electrons very much. So we know that those particular elements are really unreactive.
Right. So that's your helium and your neon and your argon and so on. What are called the
noble gases.
The noble gases, and they're noble because they're sort of aloof and standing off, saying, no, I'm not going to react with you. Thank you very much. So there's all these different ways of putting these things together into the periodic table, and that's what was, at least in its initial form, put together 150 years ago, and that's worth celebrating. But it's not just finding out the structure of all the stuff around us. There's actually some really interesting astronomy in the periodic table as well. So let's find our way into that. Emily, where do we start?
Well, I think a really good place to start is actually a quote from Carl Sagan. Because
it's always a good place to start.
Always a good place to start. So I'm going to read the quote. It says, "The nitrogen in our DNA, the calcium in our teeth, the iron in our blood, the carbon in our apple pies, were all made in the interiors of stars, collapsing stars. We are made of star stuff."
Very nice, Carl. And I like the fact that he got a little bit of American apple pie in there as well. He speaks for all of us, but mainly for the Americans. So thanks for that. Yep. Okay. So what he's saying is all the stuff that we see around us, all the different kinds of atoms and all the different elements are formed in stars, in collapsing stars. We are made of star stuff. What's he talking about?
So we're talking about, actually, if you come down to the atom level, how do you make an atom? Well, the very, very, very overwhelming majority of all atoms in this entire universe were made in stars or related to things that stars do.
Right. Okay. So when he says we are made of star stuff, what he means is that all the stuff that we're composed of, all the things that we can see around us, ultimately we can trace back to things that stars do that gave us those elements.
Yeah. So those elements originated in stars, which is a really cool idea, really.
Very cool. All right. So I'm looking at this periodic table that you've got on the table here in front of us, and I will put an image of that up on the website, up on the in the show notes. Let's start at the very beginning of that, the very first element on the periodic table, the simplest one. It's just one proton with one electron going around the outside of it. It's hydrogen. And you've got that circled, and it says hydrogen, nearly everything. All right, let's start there. What do you mean by that?
So this is an astronomer's periodic table.
Right, okay.
Right? Now, it's actually color-coded by where the chemical elements come from. So we've got different processes that we're going to go through, that we're going to talk about, all the different places that we can form different chemical elements. And so it's color-coded by that, and it's actually shaded. So some of the elements can be formed in more than one way. So it's shaded kind of about what fraction were formed in each of the ways. And if you really want to go down to the nitty-gritty of what astronomers care about mostly in the universe. And so the thing that astronomers get quite a lot of flack for is the way we classify brutally the periodic table. And the way we do that is looking at the universe, we have hydrogen, we have a little bit of helium, and then everything else in the periodic table we call a metal, because it's...
Even though it's demonstrably not.
Even though it's not. And a metal has a very specific chemical meaning, and the chemists get really annoyed when we call things like calcium a metal. But it's because it's so insignificant, at least proportionally to the amount of hydrogen and helium, it's just kind of, you have hydrogen, helium, and metals.
That's all you've got. Okay, so on your astronomer's periodic table here, very special one. So we start with hydrogen, which is nearly everything, and we've got helium, element number 2, which is labeled everything else.
Everything
so,
else.
Okay, we need to start with this, and we need to unpack this. Nearly everything and everything else. Talk us through hydrogen and helium from an astronomer's point of view.
Well, hydrogen and helium, most abundant two species in the universe.
Like to what degree?
Oh,
like 90%?
99.9. Well, it depends if you do it by mass or volume. But
okay.
Yeah, they're hugely, overwhelmingly the two most abundant.
So the vast, vast majority of everything in the night sky, everything in the universe, is hydrogen and helium. To a good approximation, that's it.
Yeah.
That's the lot.
Which is quite strange because that's not the same as on Earth,
No.
for example.
No,
But we
that's
have to
quite
think,
different.
We have to think universally in
Right.
the really literal sense of the
Okay.
word. Right?
So we need to step outside of the bounds of our planet and think we're just a little bit of a special little corner of the universe. The rest of the place isn't like this. It's mostly hydrogen and helium. Okay, so where'd all that come from?
Well, they're also the oldest two elements.
Right.
They go all the way back to the Big Bang. So the process that we formed hydrogen and helium is called Big Bang nucleosynthesis.
Good term. Big Bang. So that's the beginning of the universe where everything just went whoosh out of a singularity, and we'll talk about that maybe some other time. That's really complicated. But the Big Bang, lots and lots and lots of energy, which eventually formed particles, which eventually, this soup of protons and electrons and stuff, and then it eventually expands enough and cools down enough that you can form atoms, but only the simplest ones. And the simplest one is a proton and an electron going zip, we can stick together. That's an atom. That's hydrogen. That would have been pretty much everything, except that you can whack a couple of hydrogens together to make some helium, can't you?
Yeah, and that was basically what happened or most of it happened in the first 3 minutes of the universe. And, well, with a little bit of expansion and cooling, we had about 20 minutes to form what we call Big Bang nucleosynthesis elements.
Now, I'd like to just take just a moment to just let that one sink in, folks. We're talking 13.8 billion years ago, and Emily's talking with great confidence about what happened in the first, say, 3 to 20 minutes of the universe. But that's how physics goes at the moment. We can work backwards and with reasonable confidence predict these things.
Because we can model basically the temperature that sort of big soupy mess of protons and neutrons and electrons had to be. And once you start expanding and cooling, you very quickly at the 20-minute mark reach the point where you can't stick atoms together in this nucleosynthesis anymore because you're too cold, basically. So we only get the first 20 minutes minus 3 minutes to stick together these elements. The overwhelming majority is hydrogen. You get quite a reasonable chunk of helium is in there as well, and tiny little bits of other things like beryllium as well.
Right, the next couple of levels up. But then once it's cooled enough, you're not getting that kind of fusion anymore. In the heart of stars, in the heart of the sun, you've got huge temperatures and pressures which are squeezing these things together, and hydrogen can turn into helium, and hydrogen and helium can turn into other things. But that's in the core of a star. Eventually, after 20 minutes, the universe had cooled enough where, actually, you know what, we can't do this anymore. There's not enough energy. And so hydrogen, helium, tiny amount of other, and then that's it. That's what we've got. The universe is now filled with hydrogen and helium to a large approximation.
Maybe a couple of metals.
Maybe a couple of metals, a couple of other bits. Okay, so that's it. That's our starting point. So we've got nearly everything and everything else, and then a little bit of just, rounding error. Okay, what happens from there?
Well, we're going to see this nucleosynthesis term crop up a few times. So it's worth saying that you're right, it is a fusion. That's the basic process that we're looking at. When we talk about nucleosynthesis, what we're also acknowledging, I guess, is that it's not quite so simple as smash two bits together and you get a bigger bit. There's actually cyclic processes that go on. There's lots of really interesting chains of reactions, and how much material there is in different chains and different parts of the cycles, how long it takes different steps in the cycle to happen. Those are all really important, and there's still things that we're measuring today. So nuclear astrophysicists, for example, are really interested in knowing things like how big atoms are, how likely they are to smash together, and therefore, what are these chains, what are these really complicated processes. So we've got nucleosynthesis as kind of this fancy word to describe a whole series of different nuclear reactions going on, including fusion. It's
fascinating because the energy, the little dance of energy that's involved in these things, as you said, it's not just a matter of taking two small things, bashing them together, and hey, you've got like bits of plasticine, smack them together and you've got a bigger piece of plasticine. No, it doesn't quite work that way. And there are very subtle shifts in energy when you try to combine one nucleus with another nucleus, and it'll spit out a bit because that's just a bit too much. And if you don't go through the right path, you can't get to a particular element. It's a fascinating journey. No wonder it's taken quite a long time to actually figure a lot of this stuff out. So as we work our way up through the periodic table then, we had hydrogen, which was nearly everything. We've got helium, which is pretty much everything else. The next one on the table is lithium, and that's got multiple colours on your periodic table, which means, from what you said earlier, it can be formed in multiple ways. So we're now getting into the interesting part of the table, into the metals. So what's happening here?
So the table is super complex, but we're going to generalize.
Okay.
So the first bit of the table, so let's say if you're looking at it, it's the colors up to kind of the end of the yellowy bit. If you're thinking about numbers, then we're going up to the chemical element of maybe 20 to 30, kind of in that area.
So we've gone through carbon and nitrogen and oxygen and all the way up to sort of, say, around titanium, vanadium, iron. We're getting up into that kind of area.
Yeah. And so we can broadly call these couple of rows in the periodic table star poo.
Star poo, okay. All right. What do you mean? What?
So these are chemical elements that were formed inside stars, and they kind of just get left over once the star has died.
Okay, so the excreta of stars, star poo, that makes it sound not terribly pleasant. They don't get ejected from stars. They're still hanging around inside the stars?
Yeah, so particularly the elements, so we're talking about 6 to 26, which is carbon, all the way up to iron. Those are formed in the very sort of standard, what we call stellar nucleosynthesis reactions. So this is a star is going to be fusing hydrogen to helium, and then it goes towards the end of its life, it starts fusing higher and higher elements because it runs out of hydrogen. So it sort of takes the next best thing, which is helium, and then it runs out of helium, so it takes the next best thing. And it tries to keep itself alive by fusing heavier and heavier elements, sometimes in some really complex cycles, to try and keep itself going.
Now, that makes it sound very, anthropomorphic. It sounds like the star is going, I've got to quick, find me some stuff. I need to fuse it together. What's actually happening from a physics point of view is that, a star doesn't have to fuse stuff together. So what's the mechanism here? And it's that even though it might sound a little counterintuitive, if you bang a couple of atoms together, a couple of light atoms together, if the product can be lower in energy, right? If you take some hydrogen and it can form in an interesting fusion way some helium, which is a larger chunk of atomic stuff, of nuclear stuff, that's lower in energy. And so it's energetically favorable to do that. If you bang a couple of lighter atoms together to make, oxygen, that's lower in energy. It's energetically favorable to do that, which means that if you've got enough stuff bashing together, eventually that is going to happen. Turning hydrogen into helium, if there's lots of hydrogen around, then there's plenty of possibilities to do that. Once you run out of hydrogen, you run out of helium, you've still got lots of stuff bumping together, which can energetically turn into other things through these nuclear fusion processes. And that can keep going on and making bigger and bigger things, putting out more and more energy until eventually, you've made the entire periodic table?
No, you run out, unfortunately.
So you run to the end of that line.
So the reason why the star kind of has to do it, if you like, is because it's got to hold itself up against gravity. And it can only fuse things together and output energy to hold itself up against gravity until it reaches about iron, maybe a couple of species beyond that.
So the gravity's squeezing down, and when it squeezes down, it makes everything incredibly hot and dense, and those nuclear processes take over, and they keep going, if you like, pushing out against that gravity. I mean, the gravity's really heating things up, and those processes will keep going until there aren't any processes left.
Yeah, because beyond iron, you don't get energy out if you put two heavy nuclei together.
Right. Okay. So at that point, it starts becoming energetically unfavorable. So does that mean if you do try to bash some iron with something else, you might get something bigger, but then that would fall apart and go the other way. It'd start coming down
you need to
again.
put energy into it.
Yeah.
So the star's no longer producing energy to hold itself up against gravity. So this is why on my diagram I labelled it iron as the star killer.
Ah, okay. So right there in the middle of the periodic table, iron, the star killer. So that's, give or take, that's as far as you go in what did you call it? Nucleosynthesis?
Stellar nucleosynthesis.
Stellar nucleosynthesis. Iron is the end point. That's the star killer. And what happens there? The stars burn through everything else. It's made a lot of iron. But what happens at that point?
So depending on how big a star it is, it will basically end the final phases of its life. It will, it can't hold itself up against gravity. So if it's a fairly small star, then during the kind of later stages of its life, it's probably thrown off a lot of its outer layers through big pulses and exciting things happening on the surface. And then it eventually just blows away all of its atmosphere, and you're just left with a very small core, which has no energy production anymore. So it's just going to cool down from its initial temperature very slowly. And this is what we call a white dwarf.
A white dwarf. So are you telling me that a white dwarf is basically just the leftover lump of star poo? Is that what you're saying?
That's a bit of star poo.
Right.
And that's got your carbon, nitrogen, oxygen, all these things that the star was fusing until it ran out of energy, basically.
Okay. But all the other stuff, a lot of layers around the outside, have been blown off into the void to go and spread out throughout the universe and maybe ultimately start making other things.
Exactly. And they'll take some of those elements that the star was fusing with it. So if you only started with hydrogen and helium in the Big Bang, then the first stars were only made of hydrogen and helium.
Right, that's all you've got.
That's all you have. And then they were able to fuse, things like nitrogen and all that kind of stuff. And then once the first stars were probably big explosions, right? We're probably talking about very, very large stars that really exploded and supernova pushed out all this material back into the space between stars, the interstellar medium. That got swept up and formed the next generation of stars.
So the next generation of stars would already be forming with hydrogen and helium, but a bunch of other stuff as well.
Yeah. So all the stuff that the star was able to fuse in its core as well.
Zirconium, lutetium, vanadium, and lanthanum, and osmium, and astatine, and radium, and gold, protactinium, and indium, and gallium, and iodine, and thorium, and thulium, and thallium.
But it doesn't stop there.
Okay, because we've got as far as sort of iron, which is element number 26, out of we can go all the way up to 118, but the last 10 or so of those or more have only ever been made in accelerators in the laboratory and that kind of thing. So we can ignore them, but that's not even, that's what, a third of the way, a quarter of the way to the end of the periodic table? There's a lot left over. So there's more to this story.
There is more, and it gets really exciting from here as well.
Okay.
So the elements, basically silicon to nickel, so that's 14 to 28. Mm-hmm. Now that kind of forms part of the boundary that so it overlaps here.
Yeah.
But a lot of those elements are also formed, particularly the ones that are heavier than iron, are formed in these enormous supernova explosions.
Okay. All right. So just remind us then, what are the conditions for a supernova as opposed to not a supernova?
So you need to have a huge mass of a star, basically 8 times the mass of the sun as a beginning point. And then when a star that big reaches the end of its life, instead of shedding its layers and becoming a cooling white dwarf, the core is actually far too big to hold itself up against gravity.
So it's not just gonna sort of fade out with a whimper. It's going to go out with a bang.
It's going to go out with a bang because
right.
That core is going to very rapidly shrink. There's all sorts of wonderful processes that go on. That means that the core kind of collapses and shrinks and shrinks and shrinks and shrinks. If it's a sort of an 8 to 10-ish or 12 solar masses, then you're looking at forming a neutron star, which is a super, super, super dense version of the core. So white dwarfs are quite dense. Mm-hmm. Neutron stars are super, super dense. Much
more dense. And so super dense and super... I mean, that's a good transition to a completely different kind of material, isn't it? It's almost like a nuclear soup that the star becomes, in essence, like one big atomic nucleus. And so is that what ultimately causes a supernova, is that's shrunk down and formed this really very quite hard ball at the center of the star.
Yeah, I always like to think of it as a bit like a cartoon where you've lost all your energy, so the core kind of starts shrinking, but the outer layers of the star don't know that the core started shrinking.
Right. So
it's a little bit like a cartoon character running off the edge of a cliff and taking a while to realize that
doesn't know it's supposed to fall yet.
There's no ground beneath them, right? So the outer layers of the star don't know that the core is shrunk for a little bit, and then when they do find out, because gravity is communicating to them that suddenly things are happening inside, the whole outer atmosphere shrinks down and then starts to bounce off the core. And this is the enormous explosion of the supernova, that you get the shrinking, the bounce, and then this huge ejection of material out into space.
And this is huge. I mean, let's not make any mistake about this. This is a massive explosion. I mean, I've heard it said that a supernova can outshine the entire rest of the galaxy that it's in for relatively short periods of time, but that's a hell of a lot of energy.
Exactly, and it's that real energy production that's important for this process, because all that energy can go into smashing together these heavier elements. They can suck in a little bit of that extra energy and form much, much bigger elements.
Right. So the rest of the periodic table, all of these really heavy elements, we're going up sort of beyond iron, up into, copper and zinc, which are not much further up, but we've got, yttrium and molybdenum and Rutherford and all of these way up through the periodic table. they're being formed in this massive explosion where in the ordinary interior of a star, which is doing its fusion thing, there's like no way this is going to happen. You'd have to suck up way too much energy to do this. But suddenly in a supernova, hey, we got plenty of energy. What do you want to make? Do you want to make this stuff? Fine, we can make that stuff. Let's get one of these and whack them together, and suddenly you've got a really big element. And that's where all of that comes from in a supernova.
Yeah, and we can call this kind of bottom half of the periodic table basically star remnant poo.
Star remnant poo. So we've got star poo, which is all of the heavier normal elements like iron, and then you've got star remnant poo, which are all the really big and typically quite radioactive elements that we do see around us in the world.
Yeah.
Cool.
So that's really, really quite exciting. And we can see this, and we have actually observed the gamma rays coming from very, very heavy elements in, for example, supernova 1987A. Mm-hmm. And so we know quite a lot about what elements are being produced in supernova based on the types of radiation that they're producing after they've been formed.
That's really cool. I mean, we see around us here on Earth in this funny place that we live on, which for so many years we thought was normal, and then we realized actually no, vast majority of the universe is actually just hydrogen and helium, and that you're pretty strange Earth. But we dig out of the ground all these strange elements like uranium and go, where'd that come from? Where could that possibly come from? And then you look at a supernova, as you said, like 1987A, which was a supernova that we spotted in 1987, hence the name. And you're saying that you can actually see things like the radioactive signature of uranium in that remnant.
Yeah.
That's cool.
It's very, very cool.
And so that means that the composition of the Earth is star remnant poo. That this is
remnant poo.
We've formed from the stuff that's left over from exploding stars.
Yeah, yeah. And even more so, because this is the brand new result, and this is why this periodic table got updated a couple of years ago, is it gets even better.
Okay.
It gets even better.
Because that was good enough.
Because that was a lot of energy, right? The
Yeah.
supernova itself was a lot of energy. But there are some events in the universe that have even more energy.
Okay, more than supernova. So how big?
So remember back to 2016 when we first had a go at looking at some of the most energetic events in the universe, and the way we detected them at first was via gravitational waves.
Yes, the first detections of the gravity waves with the LIGO detector. We're talking about colliding supermassive black holes.
Those were the first things we discovered.
Yeah.
And then later, I think it was the second discovery or the third.
Anyway, early discoveries.
One of the very early discoveries.
Early days for LIGO.
Was we actually got to see two neutron stars merging together.
Yeah. So these are neutron stars, or in the first one, black holes. Neutron stars orbiting around each other very close and slowly but surely losing their orbital energy, getting closer and closer and closer until they eventually collide and combine. And that's stupidly energetic, because a stupidly energetic event is the only thing that we have a chance of seeing at this point in terms of gravity waves. So how much bigger than a supernova are we talking about? A lot, yeah.
A lot
really
bigger. Because imagine you've got two giant balls of super dense neutrons and you're going to smash those two together. And we actually got to see the afterglow in this, from different telescopes around the world as well. So we didn't just have the gravitational waves. We had lots of observations from telescopes as well.
So something that energetic, what does that give us in terms of the periodic table?
Well, we were able to understand a lot of the bottom half, if you like, of the periodic table, where or how, at least what fraction of those elements are caused by these neutron star collisions.
Right, okay.
And it's quite a lot.
Right.
Quite a lot.
So up until that point, there was perhaps a bit of an assumption that, well, all of this stuff presumably comes from supernova explosions. It's not an easy thing to study, I would imagine, waiting for a supernova and then going, quick, look for plutonium. But you can get a bit of a sense for where these things are coming from and in what proportions with the more information that we're getting from the gravitational waves.
Yeah. So if you're looking at the table, then we're looking from niobium to plutonium. Mm-hmm. So this is 41 to 94.
Okay, so we're getting right up there.
Yeah. So these are the ones in these neutron star collisions. It's really, you need a lot of energy, and you need that energy to transfer between the particle or between the atoms very, very quickly. So it's a very rapid process. And that's how you get these that's how you get these super heavy elements forming. So it was a GW 170817, the gravitational wave detection that actually helped us nail down the fractions, at least, of these elements that we're finding out there in the universe.
Wow.
Or where each of those elements is being formed.
So that's a really interesting part of this whole new branch of astronomy, this gravitational wave astronomy that's opened up just in the last couple of years, is not just about testing, Einstein's theory of relativity and how that plays out in the universe in terms of gravity waves, but also, you know what, these are really energetic events. That can teach us a lot about where the stuff comes from, all the way up to the heaviest naturally forming element we've got, which is plutonium-94. Everything beyond that, americium and beyond, all the way up to 118, they're only seen in colliders and laboratory experiments. Wow, that's cool.
It's really cool. And if you think about then the summation of where all the elements in the universe have come from, they've come from enormously nasty, big explosions or the cores of stars. I mean, these are not lovely places to go and have a picnic, right? These are some of the most energetic environments that we've had in the universe and ever will have in the universe. And the summation, I think, is that most of the stuff we have in the universe can be summed up as either Big Bang poo, star poo, or stellar remnant poo.
I don't know. I kind of like Carl Sagan's version better. Well, that does bring us to the end of this periodic table-tacular episode of the Syzygy podcast. Emily, I don't know. I'm still pretty uncomfortable with this whole notion that humans and everything around us and everything that we love is just universal poo. But I guess we can just go with that. If you have an opinion out there in the internet about that particular concept and you'd like to get in touch with us, Emily, how should they do that?
Well, first of all, you need to catch us on Twitter.
Yes, on Twitter @SyzygyPod.
That's right. And if you follow that through as well, you'll be able to see brand new episodes when they're posted. You'll be the first to know via Twitter. But you can also find out that through our Facebook page.
Yes, indeed.
So if you go and have a look on Facebook and just search for Syzygy Podcast, you're gonna come across.
You'll find us. Or if you want to go directly there, facebook.com/SyzygyPod. Basically, if you're in doubt, just see if you can find us as SyzygyPod, and that's probably us. We're on Instagram as well, SyzygyPod. You can go and find us there. And the other way that you can get in touch with the show and that you can actually help the show, if you enjoy what we do and you want us to help us do it even more, bigger and better, is you can get in touch with us through Patreon. You can become a patron of the show. Patreon.com/SyzygyPod, of course. And you can go and sign up to throw a little bit of cash our way to help us do what we do. What does that mean? It helps us to keep the lights on, basically. It helps us to keep the website going. It helps us to keep the podcast going. If we get enough, it helps us to travel to South America in 2020 to go and see an eclipse. But hey, you never know your luck. So that would be an awesome thing for some of you to do. But the other way that you can help us is just by simply talking us up. We'd love to grow the audience. We want to reach as many people as we possibly can to talk about the great stuff that's out there in the universe. So tell your friends, tell your family, just tell the world. Give us some reviews on your podcast network of choice, and we'll be forever grateful. Otherwise, we'll be back again in another week or so for the next edition of Syzygy. We made it to episode 30. I'm not quite sure how we did that.
Yeah. And I promise in the next episode I won't call you a pile of poo.
Thanks, mate. Catch you next time. Just poo. See, if Sagan had said that on his show, it would never have been picked up for a second season. Not a chance.
Well, we're used to this idea of being so romantic about it.
We are, and basically we're just the caca of the universe.
The leftover bits. The useless bits that stars don't need anymore in a lot of cases. They really want the hydrogen.
Yeah.
They don't want us.
The hydrogen and then the helium so they can talk money.
There's sulfur, californium, and fermium, berkelium, and also mendelevium, einsteinium, nobelium, and argon, krypton, neon, radon, xenon, zinc, and rhodium, and chlorine, carbon, cobalt, copper, tungsten, tin, and sodium. These are the only ones of which the news has come to Harvard. And there may be many others, but they haven't been discovered.